Good morning, everyone. I welcome you all for today's session. So, in today's session, we'll be studying regarding fixed cylinders and the equations which are used to calculate the stresses in fixed cylinders. Right. So, we already know what are fixed cylinders. Fixed cylinders are the pressure vessels where the R by T ratio is less than or equal to 10. R by T ratio is less than or equal to 10. If it is greater than 10, then it comes under the category of thin cylinders. Right. So as of now, it is less than or equal to 10, and that is the reason I call them as fixed cylinders. Right. The next thing is what are the important stresses that are coming in fixed cylinders. So in fixed cylinders, there are three stresses: longitudinal stresses, circumferential stresses, and the radial pressure or the radial stress. So among these three, two are most influential. First one is circumferential stress, and the second one is radial pressure or radial stress. These two mostly influence more when compared to the third one. Right? So first, let us try to understand how to calculate the circumferential stress and a radial pressure in case of a fixed cylinder. Right? So in order to calculate these, how the circumferential stress and the radial pressure varies along with the thickness of the fixed cylinder, we are making use of certain theory or certain equations named as Lame's theory. Named as Lame's theory. That is what I have written here for the people. The variation of circumferential and radial stress along the thickness of the wall is obtained by is obtained by Lame's theory. Right, so I told you there are two influential stresses in fixed cylinders: circumferential stress and a radial stress. If you want to calculate both of these along with the thickness of the wall, then it can be obtained using the theory called as Lame's theory. So now let us study what is Lame's theory, and let us check out how I have used this theory in order to develop the equations which are used to govern the fixed cylinders. Right. So in Lame's theory, there are two important assumptions. So the first important assumption here is the shell is made up of homogeneous and isotropic material. The cylindrical pressure vessel or the shell is made up of homogeneous and isotropic material. So this is the first assumption. Second very important assumption is the longitudinal strain will always remain constant. The longitudinal strain will remain constant and is independent of radius of the shell and is independent of the radius of the shell. These two are the important assumptions which we have assumed before I could start with the derivation part. So let us begin with the derivation part. So in order to start with the derivation, I have considered a pressure vessel. I have considered a pressure vessel which is a closed container, which is a thick cylinder. So the outer radius of the thick cylinder is taken as R2. The inner radius is taken as R1. So it is a hollow cylinder, and it is a case of a thick cylinder where R by T ratio is less than or equal to 10. So the inner radius is taken as R1, outer radius is taken as R2. Then I have considered an element. I have considered a ring element. I have considered a ring element. So this is the ring element, or you can just call it as ring. So I have considered an elemental ring whose thickness is dx, and whose radius is x from the center, whose radius is x from the center. Right? Now, if there is some fluid existing here in this part, if there is fluid existing here in this part, that is at the center or the inner surface of the closed cylinder, which is a thick cylinder, then that fluid or that particular liquid is going to exert some pressure on the inner walls of the cylinder. I repeat, whenever there is a fluid which is stored at high pressure inside this closed container, it will exert an pressure on the elemental ring or the inner surface of the cylinder. So that pressure I have shown it as Px. That pressure I have shown it as Px. So this is nothing but internal pressure, internal pressure, right? And this internal pressure always acts at 90 degrees to the wall surface. It always acts at 90 degrees to the cylindrical wall surface. So Px is also called as radial pressure. Px is also called as radial pressure because it is acting along the radius. Right? Now, since it is an elemental ring, internal pressure is Px. Now, there is some external pressure which will be acting on the outer surface of the cylinder. Okay. Now, here, since I consider an elemental ring, that pressure I will be taking it as the outer surface of the elemental ring. So, that is Px plus dPx. That is internal pressure of same magnitude, plus some change. dPx is nothing but change in pressure. So I am calling it as change. So this change may be positive or this change may be negative. In general, I am taking it as some change in pressure when compared to the internal pressure. Right? Now, if you are going to take a section here, if you are going to take a section here on this part, so let me show you. We are going to take section here in this part. So here in this part, if I take a section, if I cut it like this, I have shown the section in both the diagrams now. You just check out. This is the section XX and I have shown it here also. So what happens in this case? So that I have shown in this figure. Right? I have taken a section, I have cut it, and the view, the top view of that I have shown in this diagram. So let us check out what are the things. So here you can just observe the top view of the cut section of the cylinder. Its length is L. I told you the element is at a distance of x from the center. So if you take this as the center part, on this side you are having x and on left side you are having x. So the total diameter becomes 2x. The radius was x, so the diameter became 2x. Thickness of the element was dx. Right? So therefore the outer diameter of the element will be 2x plus dx. 2x was the inner diameter and the thickness is dx, so the outer diameter becomes 2x plus dx. Right? So now I need to calculate bursting force. I need to calculate bursting force. So bursting force is given by internal pressure into the area on which this pressure is acting. So you can just check out where internal pressure is acting. So Px into area. So this is nothing but the area where the pressure is acting. So let me write it for you people. So this is the area. This is the area where the pressure is acting. Now, once again, this is also the area where the pressure is acting. The other two things are pressures. So this is the internal pressure, this is the external pressure. So when you are saying force, it is pressure into area. So pressure into area will be giving you force. Right? So let me go ahead and check out what is the area. So Px will be acting on Px will be acting on this rectangular area. Px will be acting on this rectangular area. I'll just draw here for you people. And then this is the area on which Px will be acting. Right? So in this rectangular or projected area, what I can say here is this distance is how much? Distance is L, right? And this distance is 2x. This distance is 2x. So this is the rectangular area where your pressure Px will be acting. Where your pressure Px will be acting. Right? So area of the rectangle is length into breadth. In this case, length is L, breadth is 2x. So the area becomes 2xl. Area becomes 2xl. And that is what I have written for you people. If you just check out, just check it here. Area I have written it as 2x into L. So the pressure which is acting outwards, I have taken it as positive. The pressure which is coming inwards, I have taken it as negative. Right? So minus sign indicates this Px plus dPx is acting in a direction opposite to Px. So Px internal pressure or radial pressure I have taken it as positive and the outer pressure is taken as negative. So the area on which this pressure Px plus dPx is acting is given by same thing. 2 is present, L is present. So for the outer fiber, the diameter will be x plus dx. So this intermediate term x will become x plus dx. So it is 2 into x plus dx into L. Also, also the resisting pressure, okay. Once if we calculate the bursting force, next let me calculate the resisting force. So the resisting force in this case will be generated because of the circumferential stress. Resisting force in this case will be because of the circumferential stress. So whenever I say force, we know that sigma is equal to force divided by area. Force divided by area. So this we are already knowing. In this case, it is circumferential stress, so it becomes sigma c. If you are require force is required, if force is your requirement, then you can take it as Fr. So you cross multiply these two things, that is area into sigma c. If you are just cross multiplying these things, it is sigma c into area on which the circumferential stress is generated. So if you just check out the area on which circumferential stress is generated, so let me show you people. So let me draw it for you so that things will be clear. Thinking of this sort, I'm drawing the cut section. So drawing may not be that clear, but I can convince you people something of this sort, right? Something of this sort. Now, this will be the area on which your circumferential stress will be acting like this. It should be here also. So whenever you have taken a cut section, so this strip will be coming here. So what I can do here is I can show you the strip as well. So let us say there is some strip here. Right, so this green color strip is having certain thickness dx. So that thickness dx I have already shown you people. Now I need to calculate the area of this strip. I need to calculate the area of this strip because your circumferential stress. So this blue colored thing I call it as circumferential stress sigma c. It is acting on this strip. So strip is rectangular in nature. It is observed from this figure. What is the area of rectangle? Length into breadth. So what is the length of the strip? The length of the strip is equal to L L into into what is the thickness of the strip? Thickness of the strip is dx. So dx. So length into breadth. So dx is the breadth, L is the length. But the thing here to be noted is the strip is on both the sides. Here also you are having the strip and here also you are having the strip. So I will be multiplying this by 2. I'll be multiplying this by 2. So the area on which the circumferential stress is acting is 2L dx. 2L dx. 2L dx. Right? So you can just observe I have taken the same thing here. It is 2L dx. So here in this case, now bursting force will be your action, resisting force will be your reaction. If this six cylinder has to be in equilibrium, then both of these forces have to be equal. Both of these forces have to be equal. So I equate both of these forces. So by equating these forces, I'll be getting this equation. I have equated the expression for bursting force and the expression for resisting force. So common terms, you can just write these terms out. So 2 is present in each and every term, so 2 can be cancelled. Also L is present in each and every term, you can cancel the term L, right? And then you open the bracket. So here you are having Px, so it is Px into x, so that term I have written it here. Next you open the bracket, you multiply these two terms, so it is once again x into Px with a negative sign. So minus into this plus it will be minus. So px into dx. So in that term, so after opening this bracket, I'll be getting two terms. So both the terms I have written here. Once again minus into minus dpx into x. I'll be multiplying these two terms. So it is minus dpx into x. So minus into plus sign. So we are having a minus sign. So it is multiply these two terms. So it is dpx into dx, that is equal to sigma c into dx. So after cancelling all the common terms, you'll be getting this equation. So neglecting higher order terms. So here when I say higher order term, I'll be taking this term dpx into dx as a higher order term. So you can just observe this dpx into dx. dpx is also a very small value and dx is also a very small value. So let us say it is 0.005 into 0.005. So the value or the product what you are getting when you multiply such small values is very, very small. Okay? Multiplication of smaller values will be still smaller, or the product of smaller values will be still smaller, and that is the reason we can neglect this term. So neglecting higher order term we get. So if we are neglecting this term, what will be getting? So this xpx and xpx are going to cancel. So the remaining term will be sigma c into dx is equal to this term minus px into dx and minus x into dp. So I need an expression for sigma c. So we keep sigma c on one side. I need an expression for sigma c. So you keep sigma c on one side, and this was what you are getting. So if I take these two terms, if I take these two terms, if I take these two terms on the right hand side, sorry, on the left hand side, it will be equated to 0. Divide this entire equation by dx. So that dx and this dx are going to cancel. So it is sigma c plus px plus x into dpx divided by dx is equal to 0. So I'm interested in what? I'm interested in finding circumferential stress. So keep it on one side, rest all terms you shift to the right side. So this you take it as equation number 1. This you take it as equation number 1. So that is the initial stage or initial first half of the derivation part. Now, as I already told you, there are three stresses which are coming in the thick cylinders. First one is the radial pressure, which is compressive in nature. So I have already shown you. You can just check out this figure. So this figure will directly indicate that radial pressure are compressive in nature. Right. So the outer forces are acting towards the center, inner forces are acting away from the center. When two forces are acting towards each other, then you can call them as the compressive nature. Right? They are compressive in nature. And the other two stresses will be tensile in nature. So circumferential stress will be tensile in nature, and even the longitudinal stress will be tensile in nature. So from generalized Hooke's law, we know that epsilon L, that is longitudinal strain, is given by sigma L by E minus nu into sigma C by E minus of minus nu px divided by E. So here you need to know this nu is nothing but Poisson's ratio. In some textbooks you have taken it as 1 by m, or in some textbooks you will be taking it as gamma. Right? So all these three cases are same. It indicates Poisson's ratio only. Now this negative sign is coming into picture because your radial pressure is compressive in nature. Radial pressure is compressive in nature. And that is the reason I have put this negative sign. So if I open this bracket, then this minus and this minus are going to multiply each other and the product will be positive. That will be my next step. You can just check out in my next step. So this minus and this minus will be multiplying each other, so it will be taking a positive value. That positive value are written here, mu into px divided by E, and this is minus nu into sigma c divided by E. So that is this term into sigma c divided by E. Now this term will vanish. This term will vanish. Why? I have also written the reason for you here. You can just check out the reason. Since epsilon L is constant, you go back to our assumptions. In the assumptions, I have clearly mentioned that the longitudinal strain will remain constant and longitudinal strain will remain constant, and it is not affected by the changes in the radial distances. That was my second assumption. And according to that assumption, if epsilon L is constant, then sigma L is also constant. Right? If strain is constant, then stress is also constant. And your Young's modulus is also constant. So what I can write here is on the right hand side you are having epsilon L. So this is constant. There are two terms remaining. These two terms minus mu into sigma c divided by E. So minus into minus is plus. So I got the second term. Right? So this will be equal to constant. So now again you just check out these two terms minus mu by E, in this case mu by E. Poisson's ratio nu is a constant, Young's modulus E is a constant. So you can also remove these things. What will be remaining is minus sigma C plus Px is equal to constant. So I'll change the sign now. If you are changing the sign, what will be getting? I'll be getting sigma C minus Px is equal to 2a. This constant, I'll take it as 2a. The constant which was there on the right hand side, I'll take it as 2a. So I have taken it as 2a. So therefore, sigma c is equal to px plus 2a. So this you can take it as your equation number 2. Right? Now you go back to your equation 1 and you compare equation 1 and equation 2. So your equation 1, you can just check out the left hand side is sigma c, and in your equation 2 also the left hand side is sigma c. When both the LHS are equal, RHS would be equated. So I equate the RHS. So you can just note in this case the RHS is minus Px minus x into dpx divided by dx. Right? So that is what I have written here. Px plus 2a. So this is the right hand side of equation number 2, and this is the right hand side of equation number 1. Both are equated because LHS are equal. So Px terms we make on one side. If we are shifting it on this side, it will be Px plus 2a is equal to minus x into dpx divided by dx. So the common term here, if you just take a common term, it will be 2 into px plus a is equal to minus x into dpx divided by dx. So you make x terms on one side, so it is minus 2. This equation or this term we shift to the right side, sorry, to the left side, x into x divided by dx. If you are shifting this on towards the left hand side, it will be dx divided by x, right, with a negative sign. Remaining term will be dpx divided by px plus a. dpx divided by px plus a. Right? Now integrating these equations on both the sides. If you are integrating these equations on both the sides, what we get? So integration of 1 by x is log x. So this is log x to the base e minus 2. I have kept it as it is. On the right hand side, if you just check out, it is 1 by x. The format is of 1 by x. Log of integration of 1 by x will be once again log of x. So it is log of px plus a. So when all are log, the constant of integration, also I'll take it in the form of a log. So it is log b to the base e. Right? So now we know that here this is important. I'm using the laws of logarithm. Laws of logarithm. So m log n can be written as written as log n raised to m. Log n raised to m. So that is what I have written here. Next, this is once again constant, and this is also constant. Next, you concentrate on these two terms. So these two terms, it is log a minus log b. It is of the form log a minus log b. So when you are having the difference of log a minus log b can be written as log a by b. Log a by b. And that is what I have written here. Log b divided by x square to the base e is equal to log of px plus a. Right? So it is just simple use of laws of logarithm. Once we are done with this, I'll be cancelling the log on both the sides. I'll be cancelling the log on both the sides. When you cancel the log on both the sides, what do you get? So here log and here log, I'll cancel it. So it is px plus a, px plus a is equal to b by x square is equal to b by x square. So I'm in need of radial pressure. So px I'll keep it on one side, a I'll shift to the right side. So it is b divided by x square minus a. And this you take it as equation number 3. This you take it as equation number 3. So now I'll be substituting this equation 3 in equation number 2. Right? Substituting the value of px or equation 3 in equation number 2. So let me check out what I'll be getting here. So this is my equation number 2. We just go back and check sigma c is equal to px plus 2a is my equation number 2. Value of px I have substituted here. So this is the value of px. Right? So this is px. Px is b by x square minus a plus 2a I have kept it as it is. So therefore sigma c is equal to b by x square plus a. So this is the expression for circumferential stress in case of 6 cylinders. Right? So now equation 3 and equation 4. You are having equation 3 here and equation 4. So both these equations, I call them as Lame's equations. I call them as Lame's equations. Very important. These are called as Lame's equations because of theory, and these equations were developed by a person called as Lame. So Lame's equations are the equations for circumferential stress and the radial stresses which are generated in case of a 6 cylinder. Now, since I am calling it as a 6 cylinder, the thickness is relatively significant. You need to consider the variation of stresses along the thickness. So what I have taken here is, suppose I take some center over here. So this is the radius R1, that is the inner radius, and this is the radius R2, that is the outer radius. Right, intermediate you'll be having some ring element. What all things I have considered, everything will be there. So along this thickness, so inner radius is R1, outer radius is R2, and along this thickness, how these stresses are distributed, that is important for us. So that is what I have shown. The variation of stresses is shown to us. So this is sigma I, that is circumferential stress. This is circumferential stress at the inner fiber. Sigma O, this is circumferential stress at the outer fiber. Pi is the internal pressure at the inner side, and Po is the pressure acting on the outer fiber or the outer side of the cylinder. So this is the variation of the circumferential stress and the radial pressure along with the thickness of the cylinder. Right? So that's it. So have a great day. In the next session, we'll be solving some numericals. So till then, take care. Bye bye.